Our next speaker is Álvaro Álvarez-Domi. He's a PhD student at Universidad Complutense de Madrid. And he's going to talk about vacuum ambiguities and the Schwinger effect on the quantum kinetic approach. Please, Álvaro, the floor is yours.
Well, thanks for the presentation. This talk has also been in collaboration with Mercedes Martín Benito, who has just talked, and with Luis Garay, who will talk in a few minutes. So the Schwinger effect is a non-perturbative particle creation phenomenon which happens when we couple a strong electric field to a certain matter field. So we want to study this phenomenon, and to that I'm going to consider a charged scalar field, which is equivalent to dealing with two real scalar fields in Minkowski spacetime. And the electric field that we are considering here will be classical, so no back reaction. We will neglect back reaction here, spatially homogeneous and time dependent. So thanks to this spatial homogeneity, we are going to fix the temporal gauge, and we will denote as A of t as the vector potential associated to the electric field E of t. So here we have all the ingredients to define our quantum theories associated to the classical theory. To that, let's say that each real scalar field satisfies a Klein-Gordon equation where there is an vector potential coupled. Perfect. When we Fourier transform this Klein-Gordon equation, what we obtain are harmonic oscillator equations which are decoupled between them. These harmonic oscillator equations have time-dependent frequencies because they depend on the vector potential, which is time-dependent. Great. So now, from the infinitely many different possibilities of solutions that we have for these harmonic oscillator equations, one for each initial condition that we impose, then we need to fix one particular basis of solutions. And once we have done that, then we can define a particular quantum field operator via the canonical quantization approach as the following. So you give me one particular basis, and then this defines in turn some annihilation and creation operators and the quantum field operator. So I want to remark on this idea now, on this slide, about the dependence of this procedure on the particular solutions that we are assuming. These are what we call the canonical quantization ambiguities. So the particular quantum field operator depends on the choice that we make of these particular solutions to the harmonic oscillator equations. And then when we fix them, we provide some particular annihilation and creation operators, and in turn add the vacuum of our quantum theory, which is the state annihilated by all the annihilation operators. Perfect. Equivalently, we can see this as fixing some initial conditions, putting some initial conditions to the ordinary differential equation. Well, great. So as long as we do not impose any criteria to the quantization, then the choice of vacuum is completely arbitrary. So what we do as physicists is to impose some criteria to restrict the ambiguities in the choice of vacuum. Well, one possible criterion is the preservation of the classical symmetries in the quantum theory associated to the quantum theory. So, for example, if we consider free matter fields in Minkowski spacetime when there's no electric field, then this setting has maximal symmetry. It has Poincare symmetry. So this criterion is so strong that there's only one vacuum, the Minkowski vacuum, which is compatible with the classical symmetries. So no ambiguities appear here. There's only one vacuum that is defined when we fix the basis of solutions to be in the ultraviolet as plane waves. However, what happens when we couple the electric field? When we have the Schwinger effect? Well, then we lose time translational invariance, and then we lose maximal symmetry. And the criterion of preservation of classical symmetries is then now less strong. So now we have ambiguities in the choice of vacuum. That's why we can find many different options in the literature, such as adiabatic vacua, vacua of low energy, and a large etc. to pick one particular vacuum from the arbitrary family that we a priori have. So here we are interested in defining a physically reasonable family of vacua to pick. And to do that, I'm going to define a particular magnitude, which is the number of created pairs of excitations of the field, or particles. Great. So let's plot the time evolution of the vector potential associated to the electric field in this simple setting, just to explain how we define the number of particles. Let's consider that at initial time, we have the electric field turned off. So we have Minkowski spacetime, and there's no ambiguity, as I told you before, to choose the vacuum, because we need to choose the Minkowski vacuum. So this reference vacuum has no ambiguities. However, when we turn on the electric field, then time translational invariance is broken, and we have no perfect notion of vacuum at that time. So we need to fix, following some criterion, the annihilation and creation operators. So the number of created pairs is defined as the following. What I want to remark here is that this definition strongly depends on the ambiguities, because it strongly depends on the particular choice of vacuum that we have done from the infinitely many different possibilities of vacua that we can choose. So now we would like to compute this number of created pairs. And to do that, I'm going to go to classical kinetic theory, where there's an equation, the so-called classical Vlasov equation, which is an equation, a closed equation of motion for the probability distribution of particles in a non-equilibrium system, just like the Boltzmann equation, but neglecting collisions. So in the literature, we can also find the quantum version of this classical Vlasov equation, the so-called quantum Vlasov equation, where now the number of created pairs plays the role of the probability distribution of particles. So with this quantum Vlasov equation, what we have is an integral differential equation to compute for the number of created pairs, which was what we wanted. Well, however, in the literature, the quantum Vlasov equation, which we can find, is what we call the standard version of it, because it's assumed a particular vacuum. So it's written only for one particular vacuum from the infinitely many different possibilities that we have. So what we have done in our work is to generalize this quantum Vlasov equation in order to accommodate for general vacua. And this is the expression that we have obtained. So you give me one vacuum now, and I can provide you a particular expression, a particular generalized quantum Vlasov equation to compute for the number of created pairs. Well, so now that we have this equation, let's put it aside just for a moment, and let's follow our arguments to obtain this reduced family of physically reasonable vacua. So in order to do that, I'm going to use the criterion that Mercedes has just told us before, which is the unitary implementation of the dynamics, just imposing that the vacuum that we choose has a quantum theory which allows for unitary dynamics, which allows for a time evolution operator, which is unitary. And with that, as Mercedes has showed us before, we succeed in finding a unique unitarily equivalent family of vacua, where each of the vacua inside this family leads to a finite total number of created pairs at each finite time. So we do not have an infinite explosion of particles at an intermediate time. So that's a good property of this vacua. In addition, vacua inside this family dictates have also the same ultraviolet behavior. In particular, the initial conditions that define the vacua in the ultraviolet has to satisfy this concrete behavior. However, we still have some ambiguities because we do not have one vacuum with this criterion. We have infinitely many still. So we have a parameter, we have another contribution that we can put wherever we want, provided that it converges faster than k to the minus 1/2. So the question here is, what happens if I put there a contribution which converges faster than k to the minus 1/2? Well,
Alvaro, you have 2 minutes.
Yeah, thanks. So if we put there a contribution which converges faster than k to the minus 1/2, but is slower than k to the minus 2, I study the generalized quantum Vlasov equation that I showed you before, and I expand it in the ultraviolet and study its leading order. And what we see is that the leading order strongly depends on the ambiguities on the vacua that we have chosen. And that's something that we don't really like, because at short scales, we would expect that the generalized quantum Vlasov equation, our magnitude, doesn't depend on the arbitrariness of the ambiguities in the canonical quantization, and only on the physics of the system. And that's exactly what happens when we consider vacua here, vacua with contributions which converges faster than k to the minus 2. We have exactly the same leading order behavior in the ultraviolet for the generalized quantum Vlasov equation for the leading order, which coincides with the standard quantum Vlasov equation, which is independent of the ambiguities. So we have succeeded in determining a physically reasonable family of vacua here, which at the same time include different possibilities of vacua that we find in the literature. For example, adiabatic vacua, but at the same time leaves out of this family all the physically interesting vacua, such as the Minkowski vacuum. So, as Mercedes has told us before, we cannot use plane waves to canonically quantize a theory with this time-dependent electric field. So yeah, I have the conclusions, and thanks for your attention.
Thank you, Alvaro, for your talk.
Thank you.
So we have 2 minutes for
Jose, I couldn't hear you. I don't know if the audio is going well, but I couldn't hear you.
oh, maybe the microphone. Can you hear me now?
Yes.
Yeah, you cut out sometimes.
Okay, sorry about that. So yeah, I was saying that maybe we have time for a short question. Well, I don't see any. Oh, Eduardo, go ahead.
Hello, Alvaro. How are you?
Hello.
Thank you. Nice talk. So I have a quick question about. So you see, like in basically reasonable vacua could be many things, right? Of course, you don't want the thing to explode locally, give you local divergences or other issues like that. But you know, sometimes when you have space times like Minkowski, I was thinking, right? The thing with Minkowski is that Minkowski is very clear that it's like something like a Sitter Minkowski. You have symmetries, right? And you know that the vacuum is the only state. You can call the vacuum the only state that has the same symmetries as the space-time, right? So in this case, you're breaking the symmetry. In this case, it would be time translational invariance in the field dynamics, right?
Exactly.
Couldn't you do it? I mean, typically we do it the following, right? We say, well, we consider that it's a perturbation. The degrees of freedom of the field is just a perturbation over so that the symplectic dynamics of the field, if you want, are time dependent, right? But still, there's a background, and there's no time dependence in that background. What changes here? So if you have a time dependent electric field, what is the main reason that you can have? You still have a space-time translation of symmetry, right? Is that the theory doesn't have the vacuum of a theory changes in time, and is that what's going on, in very hand-wavily speaking? And because of that, it doesn't have the symmetries. So if you do canonical quantization of plane wave quantization, right? You would have a different vacuum at every point in time, something like that. If you mind, that's what it would be.
Yeah, exactly. At each intermediate time, we have different vacua.
Right. And the beta coefficients, if you were to try to compute Bogoliubov transformations between one and the other, the beta coefficients are divergent in that case?
The beta coefficient, which corresponds to the square root of the number of created pairs that I showed you before, exploded if you get out of our family.
Perfect. All right. Thank you.
Thank you.
Right, thank you both. Let's thank again Alvaro for his talk.
Thank you for inviting me.